Hi, let's look at this work example on the different calculation for the air treatment process. So let's say you have a 0.2 kilograms per second of air passing through this particular cooling coil, all right? And before going into the coil, it has a dry bulb temperature of 28 degrees Celsius, and it has also the RH of 80%. And after passing through the coil, the temperature drops to 13 degrees Celsius and the RH become 95%. The surface temperature, TADP, apparatus dew point temperature, is 11 degrees Celsius. Alright, so this is the temperature of the surface of the coil. The chilled water supply temperature is 6.9 degrees Celsius and the return temperature is 12.5 degrees Celsius. Alright, so these are some of the information that you can fill in, and using a diagram like this will help you better visualize. Okay, let's do the calculation step by step. First, they ask for sensible load. So part A, okay, so to calculate sensible load, we shall use this equation QS is equal to m dot C air delta T. So the mass flow rate of air is 0.2, heat capacity of air is 1.005, and delta T is the temperature difference before the coil and after the coil. So the temperature difference is 28 minus 13. So if you calculate this out, you should get 3.015 kilowatts. Part B, they ask for the latent load. So latent load, the formula is QL is equal to mass flow rate of air multiplied by latent heat of vaporization multiplied by delta omega, which is the change in humidity ratio. However, we have a problem over here because we do not have the humidity ratio before and after the coil. But we are able to find out what is the humidity ratio if we use the psychrometric chart to help us. So you are going to plot these 2 points onto the psychrometric chart and retrieve the respective humidity ratio. Okay, so we shall use this X-ray psychrometric chart to help us retrieve the humidity ratio value. So the initial condition is 28 degrees Celsius. This is 20 all the way to 30. So 28 is over here. So 28 is along this vertical line and the RH is 80%. So 80% RH is over here. So the intersection point of 80% and 28 degrees Celsius will be somewhere around here. So this is the upstream condition. So maybe just label it as 0.1. After passing through the cooling coil, the temperature drops to 13 degrees Celsius. So 13 degrees Celsius will be along this vertical line because this is 10. So 10, 11, 12, 13. 13 degrees Celsius and 95% RH. So you'll be very near to the saturation curve. So somewhere over here. So let's label this as 0.2, and the process is from 0.1 to 0.2. So this is the process that is happening after it passes through the cooling coil. But don't forget, we are using the psychrometric chart because we want to find out what is the humidity ratio at 0.1 and at 0.2. So let me zoom in a little bit. Let's draw a horizontal line from 0.1 all the way to the right hand side and read off what is the humidity ratio over there. And you read off the humidity ratio, it is 19.2. Because this is 18, the next division is 18.5 followed by 19. So every increment is 0.5 grams per kilograms. So this is 19.2 grams per kilograms. How about the outlet, which is 0.2? So similarly, let's draw a horizontal line all the way to the right. And this particular point is just nice on the middle between 8 and 10. So this is 9 grams per kilograms. This is 9 grams. So from here, we will be able to find what is the delta omega by finding the gap over here. So let's continue with the calculation over here. So mass flow rate is 0.2. Latent heat of vaporization is 2260, which is the constant number. And delta omega we have just found out is 19.2 minus 9 grams per kilograms. But remember, we have to convert these to kg per kg. So you have to divide by 1000. So let me make a remark over here. This change in humidity ratio must be in kilograms per kilograms. Okay, if you compute this out, you should get a value of 4.61 kilowatts. So that is the latent load. Next, they want to find the condensate mass flow rate. So condensate mass flow rate means the amount of water that is forming at the surface of the coil. So if you refer back to the previous topic, to find the condensate mass flow rate will be equal to the mass flow rate of the air multiplied by the change in humidity ratio. So mass flow rate of air is 0.2. The change in humidity ratio is 19.2 minus 9. And if you compute this out, you will get a very small value, and the value is 2.04 times 10 to the power of minus 3 kilograms per second. That is to say, is around 2 grams per second of water that it will come out as condensate. Part D, they ask for the total cooling coil load. So the total cooling coil load will be equal to the amount of heat, sensible heat that is lost by the air, plus the amount of latent heat lost by the air, minus away the energy of the condensate water, which is the mass flow rate of the condensate multiplied by the condensate enthalpy value. Okay, let me shift this up a little bit. So sensible load is 3.015. Latent load is 4.61. Condensate of water is, mass flow rate of water is 2.04 times 10 to the power minus 3, which we have just found. Enthalpy of the condensate will be equal to the condensate temperature, which we can assume it to be same as the apparatus dew point temperature, 11 degrees Celsius, multiplied by 4.19. So this will give us the enthalpy of the water. So if you compute this out, you will get a value of 7.625, which is the total heat lost by the air, Qs plus QL, minus the amount of energy by the condensate water, which is 0.094. As you can see, it's a very, very small number, so most of the time we will just ignore this part. But for this example, I just want to show you theoretically how is it like. So if you compute this out, it's 7.53 kilowatts. Alright, part E, sensible heat ratio. Sensible heat ratio is equal to Qs divided by the total load of the air. So Qs plus QL. So it's 3.015 divided by 7.625, which we have just computed just now. Alright, so this ratio will be equal to 0.40. Part F, they ask for the bypass factor. Bypass factor, let's call it BF, is equal to temperature, the outlet temperature, which is 13 degrees Celsius, outlet temperature, minus the apparatus dew point temperature, which is 11 degrees Celsius. So 30 minus 11 divide by the inlet temperature, which is 28, minus the apparatus dew point temperature, which is 11 again. So if you compute this out, the bypass factor is 0.12. And finally, part G. Part G, they ask for the mass flow rate of chilled water. So you are given the supply temperature of the chilled water and the return temperature water, but you are not sure what is the mass flow rate. We can find this by assuming the amount of heat gained by the water is equal to the cooling coil load. So cooling coil load, as we have calculated just now, is 7.53. Alright, so Q coil is actually equal to the mass flow rate of chilled water multiplied by heat capacity of water multiplied by delta T of the water temperature. Alright, so Q coil is equal to, let me shift this up a little bit again. Q coil is equal to 7.53, which is the answer from part D. Mass flow rate of water is what we want to find. Heat capacity of water is 4.19, and delta T of water will be just the temperature difference between the return temperature, which is 12.5, minus the supply temperature 6.9. So if you compute this out, the chilled water mass flow rate will be equal to 0.32 kilograms per second. Alright, so with that, this is the one of the work example on how to use all these various equations in an air treatment process.